Our third speaker this afternoon is Stephanie Miller, University of Michigan, Field Plasmas and Nuclear Fusion Advisor Ryan McBride, and she did her residencies at Sandia National Laboratory in 2019 and 2021.
Okay, thank you very much. I think everyone should be able to hear me. Hello, everyone. I'm Stephanie Miller. Today I'm going to be talking about, what I've been working on for my thesis research, the analysis of laser preheating stage of MagLIF, which we will talk about. I know acronyms can be a lot, to increase laser energy coupling and validate simulations. Like to throw shout outs to the logos, NNSA, the LRGF. I am a loud and proud recipient of the first class of the Laboratory Residency Graduate Fellowship, as well as Sandia National Lab, who I've done my research with. Okay, so we're pretty close to the facility, actually, here in Santa Fe. The Z Machine is a facility I think some of you were able to tour a bit ago. Is a pulse power device in Albuquerque, New Mexico at Sandia National Labs. It's a really impressive facility that can do a lot of really cool science, from materials studies to fusion energy research. It has a really cool platform for studying NNSA applicable stockpile stewardship. But yeah, so it stores 22 megajoules of energy, just a bunch of, like, I think some of the highlights I like are the 26 megaamps peak current. You can kind of see the details here, but it would not be a Sandia talk if I didn't show arcs and sparks. So as you can see here is a picture of the Z Machine when it fires. It's capable of creating these really extreme conditions, right? And so in these conditions, we can study really cool science that we wouldn't have the opportunity to do without large-scale facilities like this. Okay, so the bulk of my research has been surrounding this laser heating stage here of MagLIF. So MagLIF stands for Magnetized Liner Inertial Fusion. It's a scheme, a fusion scheme that involves, we like to think of it as taking like a soda can filled with deuterium fuel. You crush it this way to try to compress on access and get fusion. So like I said, the bulk of my research is kind of in this stage, this laser entrance stage. So a preheating laser kind of enters the top of this target. So I worked on two primary projects throughout my research. One that involves this window here. So you can think of it as almost like a piece of saran wrap that stretches over and holds the fuel in place until it's time to compress. And that's where the laser enters through, as well as some later research that we've more recently been working on studying this metallic liner as this laser comes in and preheats this fuel inside. So the first project I worked on during my graduate work, the laser gate concept, gate meaning a gate that opens, not the scandal name gate. So we like to make a little note about that. It's not a scandal. But yeah, so Steve Slutz, a scientist at Sandia, had proposed this work. So normally the laser comes through, it ablates through this thin plastic window. It causes a lot of mess. You end up mixing this window material into your fuel. You get a lot of non-uniformities, which can decrease the potential for fusion yield. So the concept was, hey, instead of brute force blasting our way through this window, how about we remove the window so we can hopefully aim to couple more of the preheating laser energy into the target fuel itself, which is really important when we think about scaling these Z concepts up to higher and higher schemes where you can get more and more fusion, more and more yield, more and more energy. So as you can see here is a little top-down view of a washer. And then here is that little saran wrap window I talked about. When you pressurize inside, it does stretch and kind of bubble out a bit. And you can visually see that in some later pictures. So what we did is we wrap a wire, a thin wire, around the perimeter of that window. Then we heat that wire up, so we run current through it. I've shown it here in red. You can actually see in the videos that it does glow red when it heats up, and hopefully melt or break, loosen that window so that it pops off and is removed so that you can fire the laser in without having to interact with that window material. So this was the concept. We were very hopeful that this would work out, and spoiler alert, it does, but we'll talk about that. So here you can see me, my fingers holding for scale, these targets that we built at the University of Michigan. So you can see the little laser entrance hole, so it's pressurized, so you can see the target starts flat and then kind of bubbles up when you fill it. And then you can see that nichrome wire that's wrapped around the target. So we built these targets. So you can kind of see it here, and I'll let this video play a few times before we talk about it. So, okay, it makes a really cool sound effect. I always like to point out, through this fellowship, through my graduate work, I've had access to some incredible diagnostic facilities, incredible science facilities, but shout out to my iPhone 6 for capturing this little proof of concept video that got, I think, the funders and everyone kind of excited in this project before we went digging in a little bit further. So yeah, you can see the window kind of popping. You can see that wire glowing red. This is in the slow motion setting. So if you could hear the sound, it makes a very slow motion boom noise. But a few things that this video showed us. It showed us, one, we can open the window this way. It also showed us that the pressure from inside the target is capable of moving that window out of the way once the perimeter has been weakened. There were some potential worry spots. That wire that you see getting kicked across the entrance window, we were a little concerned what that was going to look like. But this was only 4 millisecond resolution, which is a very long time scale in the sense of MagLIF as a concept. So we wanted to do a little bit more digging into what this looked like. So next, we set up a much more robust system than my iPhone with a fancy laser, fancy camera, to do some backlighting images to be able to capture on a smaller time scale what was happening with this window opening. So I will direct you here. You can see the window and then I'll let this video, this is a series of images compiled into a video, but I'll let this play through. So now we're on 10 microsecond timescales for these images, so much more fine timescale than the iPhone images. So yes, you can see the window kind of opening up and away in the preferenced direction. So we were hoping that we could get the window to hinge in a knowable way so that it was kind of moving where we wanted it to. It is opening on timescales that were roughly what we expected for the parameters of these experiments. And you can see the window opening, coming out of the way. It stays intact. It doesn't stay on the target, but you can in postmortem see the whole circle piece of window material. You can find them in the lab. I'm sure there's still a bunch left in my lab. But you can see here that the window material kind of rides along that column of escaping gas. You kind of see a little bit of almost like a mushroom cloud as the gas expands out. So this was really promising, really exciting work that we were able to kind of prove that, yeah, we can get this window out of the way in a meaningful way. So I think that's, yeah, all I wanted to say here. Shameless self-promotion. I did publish this research. If you are interested in the nitty-gritty details of the actual math, science, all of that stuff, feel free to talk to me about it afterwards, or I would refer you to my paper. I spent my first residency working with some target fab as well as doing some other scaled experiments that I won't go into detail here. But as you can see, these were the targets I was building at Michigan, pretty big. As a newly inducted member into a target fab's world, this is much easier to build than this little tiny thing right here. So I got some practice in this size, but then was able to scale it down. So we were looking at being able to kind of scale this Michigan experiment into a more MagLIF relevant space. So we did some work in that. I'll just kind of blow through that. Okay. So then during my second residency, kind of switched projects a little bit from that window that we talked about to that wall. So same dealing still with the laser preheating stage of MagLIF. So here I'm showing a picture of Omega EP. You can see the 4 beams. So my LRGF mentor, Matt Gomez, who's in the back, he'll speak, I think, later today, had gotten the ball rolling on a lot of this project work ahead of time, and he kind of pulled me into this project. It was a really cool opportunity to be able to see the Omega space, get to use a new facility. Also really appreciative to Krell for helping fund my travel for some of that stuff. So why would we do this work here instead of on Z? There are places at the Z facility where you can study these preheats. You can get a lot more shots on Z. They kind of already had this radiograph diagnostic platform set up, as well as just increased collaboration efforts. I think something we've all been moving more towards is how can we utilize new facilities that we wouldn't typically think to study our research, just to kind of benefit the community, benefit science as a whole, figure out kind of cool, new, interesting ways to study things. So we had some ride-along shots in January of 2022, and then we went out to Omega early May to do some shots that I'll talk about here. So here you can see kind of similar shaping to the previous targets. Here was our target. So we have a laser come this way to interact with the fuel inside, as well as a laser to interact with this target to create X-rays to do some radiography. So we want to be able to study this wall movement right here. So we want to be able to look at the time that the wall is moving, the density of the wall as it expands out. Developing this radiography platform for a MagLIF space, and boosting our collaboration efforts. So here are some pictures. We had 2 primary diagnostics that I was involved in. One was this 4 Omega probe. You can think of that as just basically taking a backlit image of this wall. I have in black and white kind of traced out the wall interface. So we do a pre-shot and a post-shot. Then I have them overlaid here, and you can kind of see the wall moving. And then I have them tracked here. So during using this diagnostic, we were able to capture the time in which we think the wall starts to move when I guess I should back up, when the laser comes in and interacts with the fuel, it sends a shock wave out, and then that interacts with the walls. So we want to be able to not only study that, but also ask ourselves, are our codes able to predict this? Are they behaving the way we want, which we all know the importance of modeling and code validation, so being able to do that as well. So we were able to do pre and post shots, tracking this surface, so we can see, first of all, when does the wall start to move, as well as being able to track the velocity of that wall as it moves in time. So that was this diagnostic. And then the radiography shots. So here are 2 examples of the shots that we took. We did this resolution image with a gold mesh to be able to look at our spatial scaling as well as the profile on this beam, being able to back that out in analysis. And then here is a picture. This is the wall itself, and this is a fiducial that helps us calibrate things like the transmission and the positioning, things like that. So this resolution shot, we were very happy with the results that we got. We got data on all of the shots we were able to achieve, which in my previous experimental background is not always the case. So we were able to get a good shot series there. So we can understand this background profile as well as like spatial scaling and things like that, and look at this wall as it moves out in time. So you can see here a preliminary result that I'm still working on, don't hold me to this graph, of the time as the wall's moving. So being able to track this density profile of the wall material itself is very important. So you can kind of see in time it starts out much more dense, much more compact, and then starts to expand out later in time. And graphs like this are things that our models can generate. So being able to validate this against codes generated or plots generated by Sandia scientists that study this. So we were able to get some of this. Still working on the nitty-gritty of this analysis, but some promising results. I think it's looking like I would expect, so I'm happy about that. So what's next? We all had the pleasure of hearing Dr. Njema Frazier speak earlier. I'm moving to DC to work in her group in the NNSA, and hopefully defending my thesis very soon. Here's a picture of, I think another fellow referred to it as the before times. My last trip before the pandemic in February of 2020 to DC. So thank yous are very, very important. So we'll start out with thanking my Sandia mentors, Matt Gomez and Dave Ampliford, who are both in the room, for just everything, for helping with facility access, for teaching me how to be an incredible scientist, also for making a really welcoming space for me at Z. My university mentors, my co-advisors, Ryan McBride, who's also here, and Carolyn Krantz, for their mentorship, and just also the other grad students in my lab who I like to say were in the trenches with me through this work. And then the LRGF and the NNSA in general. I think Chris is owed a special shout out for helping me navigate all of the Krell space and helping me with transitioning to my new position, as well as this conference. I know I've been speaking to some of you about how these have been some of my favorite conferences I've attended as a grad student, and I'm glad that they're finally back in person. We'll just click through it. I don't know how much time I have, but we demonstrated proof of concept. We published on this work, did our Omega campaign. We're working on comparing to simulations. Moving to DC tomorrow. I will hopefully be graduating in the next few months. And with that, I will take questions.